Okay. So fortunately, because we did that workshop last week in unit analysis stuff, a lot of this will actually be sort of review, but hopefully reinforcing review because you've already covered it once, right? More practice, more better. So units are very important, and it'll be very tempting to leave off units when you do calculations for anything in this class. I know I used to do it all the time, but if you read the sentence, when my son was 7, he walked 3. And when he was 4, he could throw his baseball 8 and tell us that his school was 5 away. Without units in there, there's no context for, when your son was 7, what he walked 3, what? Was it 3 miles, 3 steps? Was it months old? Was it years old? Units make the difference here. And this is one of those things that when I say that you should have a ream, 500 sheets of paper that you use to do your homework on, this is why, because the units take up space. And you're going to be tempted to I want to fit everything on this single page. I want to make it look really neat and nice. And I appreciate it looking nice, but I would rather have you write in all the units and have it just be really long. So the two most common unit systems are English and metric. I think we're all pretty familiar with the English system, but the metric system is what we'll use in lab. The International System of Units, or SI units, which comes from the French, which I won't attempt. It's helpful to try and keep these units in separate categories in your mind. So length, meter, anything meter is going to be a length. We'll get into compound units later, but if you're talking about meter, make sure you're thinking length. We see gram, more specifically than kilogram. You want to be thinking mass. And we'll talk about this more, but mass is kind of like weight. On Earth, they're basically the same thing, but if you go anywhere else, mass is more accurate. Time is not often very confusing. I think we all use the same units of time, right? Seconds, hours, minutes. And then temperature, which we'll get to later again, is the Kelvin scale, which has the same intervals as Celsius, but is relative to absolute 0 rather than the freezing point of water. So remember that there's 2 separate categories for length and mass. You can't really convert between those 2. So if you're given a conversion to do and it has meters in it, let's say you want inches to meters, you know that you're only going to be working with length units. So you can ignore any conversion factors that have grams. But we'll do more conversions later. So the base units are actually based on physical properties of the universe that, as far as we know, are constant. That way, in the future, if civilization ends and we go back to the Stone Age and have to learn science again, maybe somewhere somebody will be able to say, oh, this is how they defined this length. Because if we wanted to go back, actually, as recent as the Saturn V rocket engine, we cannot build anymore because the engineers made so many modifications to the original blueprints to make things fit that if you follow the blueprints, it wouldn't work. So this is one way that we're trying to future-proof our plans or make them understandable to future people. Sorry, that was a tangent. So the meter is defined as the distance that light travels in this amount of time, right? Very, very, very tiny amount of time. So we use lasers and you can measure that. The base unit of mass, which is different than weight, is a kilogram. It's about 2.2 pounds on Earth. And this actually isn't accurate anymore. The kilogram used to be based on this very special hunk of metal in vacuum sealed containers kept under lock and key. But it's now based on some physical constant of the universe. Although it would still be cool to see the kilogram 20. So yeah, this is the difference between mass and weight. Weight is a force. So the force that your body, your amount of mass, pushes down or is pulled down onto the ground by the Earth's gravity, that's weight. It's a force. Mass is just a measure of the quantity of matter. So it's doesn't matter if you are in space where there's no gravity, or on Earth, or on Mars, or on the surface of the sun. Mass is always the same, but weight changes. So gram, kilogram, technically the base unit of mass. Gram is a much more relevant unit to this class. The base unit of time is seconds, which is based on the radioactive decay of a cesium-133 atom. And so you can take that cesium-133, and every single time that you measure this, you'll get the same amount of time for 1 second, as long as you measure 9 billion periods of the radiation emitted from it. Because radiation is one of those things that is, as far as we know, immutable. You can't change it. Things decay radioactively at the same rate forever, always. So in the English system, we have pounds, we have ounces, we have tons. We got different and seemingly unrelated words to describe different amounts of weight or different lengths, like feet, inches, yards. The SI system is actually way easier once you get the hang of it, because they use standard prefixes for everything. So if we're looking at a meter or a kilometer, a kilometer, kilo means times 10 to the 3. So 1 kilometer is 1 times 10 to the 3 meters. And there's a whole list in the book, but also in these slides if you download them, of these. So every time you see kilometer, that's 1 times 10 to the 3. If we had a kilogram, so if we had 1 kilogram, that would be 1 times 10 to the 3 grams. Or if you were to write it out without scientific notation, right, 1,000 grams. So that's one of the conversions that you had on your unit analysis workshop. So there's a whole set of these prefixes, and it can be intimidating at first, but once you get the hang of them, they're standard. So whenever you're converting between units of mass or length or even volume, when we get there, it's all the same prefixes. They all mean the same thing. Starting with things like deci. If you're working nursing or in a hospital, deciliters probably, I know, gets used. You've probably heard of centimeters just in regular life, but this is a table that would be very handy to go through and memorize. Especially these symbols and these prefixes, and then probably the multipliers here as times 10 to the whatever. The most common ones that we use are actually kilo, well, kilo, mega, and giga, and then times 10 to the -3, which is milli, times 10 to the -6, times 10 to the -9. Actually, talking about length, centimeter. Let me revise this even more for this class. Kilo, centi, milli, and maybe micro are the most important ones to memorize, because those will get thrown around the most. So you can focus on those 4 and work out from there. Sorry, I'll leave that for a little longer than that. All right. So which is the most convenient unit to express the dimensions of a poliovirus? There's about 2.8 times 10 to the -8 meters in diameter. So we wanted to express this teeny tiny number, but we wanted to use units other than meters, which are ridiculous when you think about the size of a virus. One of the ways you can do this is go back to our chart. We know that this is 1 times 10 to the -8. So we're looking for a small number. We can look at these over here, and we want to pick one of the ones that's close to it. And here, in this case, probably just go with the closest one, 1 times 10 to the negative 9. So that's going to be sort of 1 decimal place smaller than our number. So that would be nano. So if we wanted to express this in nanometers, this would be, instead of 2.8 times 10 to the negative 8, this would be 28 nanometers. And if we wanted to write out the conversion factor, we say that 1, let's do it this way. Let's say it, because this could be 1 times 10 to the negative 9 meters. Oh, I did that upside down. Meters, because we have 2.8 times 10 to the negative 8 meters. All right, so we want to convert this, so we cancel these. This will be 1 nanometer. So 1 nanometer is equal to 1 times 10 to the negative 8 meters. Grab my actual calculator for this. Oh, come on now. So I'll write on here what I'm writing in my calculator too. So my calculator can do 2.8 e to the negative 8. And then I'll do divided by 1 e negative 9. And my calculator's mad at me. Oh. All right, so then this gives me 28. And because we canceled out those units, we keep those units of nanometers. So remember, the E key makes things very convenient. Also remember, if you want to enter a negative number after E, there's a negative symbol that's different than the minus symbol, different than subtracting. Otherwise, you'll get syntax error. So derived units are formed from other units. This is a picture of my mom, actually, in Sweden or Norway, I believe, some science museum, and she's sitting in a cubic meter, right? So that's about the size of a cubic meter. One mom could fit in there fairly comfortably. So units of volume are representing the space inside of this cube. So if we were to measure every leg of the cube, they would all measure 1 meter. And so if we wanted to calculate the volume, knowing that each side is 1 meter, we multiply 1 meter times 1 meter times 1 meter. So then our meter units, if you remember from last week's workshop, we'd get 1 meter cubed. So any of these length units that we've now seen as cubed, those are representing volume, so the space inside of an area. Or square feet is a fairly common one if you're looking into apartments or houses, and that's a measure of area, right? That's how much floor space you have inside of an apartment. So these are called derived units. Liters and milliliters are sort of a special shortcut that we have for describing the derived units of volume. And 1 milliliter, capital L, is the same as 1 centimeter cubed. Those are equivalent units. So they're not technically derived units, but they're equivalent too. So this next section, we're going to talk about word problems, some strategies to solve them. Because sometimes they seem like this. If you have 4 pencils and I have 7 apples, how many pancakes will fit on the roof? Purple, because aliens don't wear hats. Duh. And I hope that it doesn't feel like I'm explaining word problems like that to you at any point, but I probably will. So there are some strategies, and especially in chemistry, there's not like set formulas. You can't just say like the area of a triangle is, whatever that equation is. I think the area of a sphere, I can do area of a sphere 4/3 pi r squared or something, pi r cubed, I don't know. Right, so there's no formulas like that necessarily in this class. Unit analysis, so what we did last week in the workshop, the worksheet that's due at the end of this week, even the lab we're going to do today, are all to help you develop strategies for doing these ultimately unit conversions that make up most of the word problems in this class. Right, like it says here, most of them can be thought of as unit conversion problems. And there will be a few specific equations that you will have to use, just a handful. So, as we know from last week, units are multiplied, divided, and canceled, just like any other algebraic quantities. Right? So if we had x, well, let's do the example of x cubed. We do x cubed and we divide it by x, then we get x squared. Same thing if you had centimeters cubed and you divide it just by centimeters once, you would get centimeters squared. So you can treat them like algebraic variables. And we can use these units as a guide to solving problems. And overarchingly, it's called dimensional analysis, because we're examining the dimensions of a thing and then converting them into dimensions or new dimensions, new units. And this is why it's so important to always write every number with its associated unit. Because if you forget that unit, or if you forget it and you start converting it into something else, you'll get a completely different and wrong number. And always include your units in your calculations. I don't really go through and grade the homework assignments, but I do look at all of them. So I can see when you're not writing your units down or when you're not writing work at all. Oh, that was the other thing I wanted to explain. Don't let me forget to explain how to look at comments on assignments in Canvas, because it's not intuitive and dumb. Okay, so anyways, back to units. Don't let them disappear or reappear. So for most of our problems, you're going to be given a quantity and asked to convert the quantity into another set of units, right? Just like we did last week. So these will take the general form that you're given information, you multiply by one or more conversion factors. Most of the ones from last week were multiple. And that will result in the information that you're looking for. Right, and so we can cancel these out to get our desired units. And this is probably the more common way that you'll see these conversion units or conversion factors, is showing which two units are equivalent. So if you have a kilometer, that's 0.6214 miles. You could rewrite that though as 1 kilometer over 0.6214 miles. Or you can flip it on its head and you can have 0.6214 miles is 1 kilometer, because it's the same length on the top and the bottom. So if we divide one length by the exact same length, we end up with 1. So it doesn't matter which units are on top or on bottom. So there will be tables like this, specifically on the unit analysis worksheet. There's a table of conversion factors for you to use. Make sure you use those conversion factors, because I know it's really easy to even just ask Siri, oh, convert this from feet to kilometers or whatever. Because you, in several of the cases, will end up with the wrong number because of the number of decimal places used in the conversion factor, or because it'll use something not quite right. The number of days in a year is one that gets a lot of people. So these may utilize prefixes, SI prefixes, right? We got things like kilo, centi. But primarily you'll get conversion factors like this. Okay, so you should all be able to do this already. So if we want to construct the conversion factors relating feet and inches, just have to know, well, how many inches are in a foot? 12. Wait, 12 inches in a foot, yeah. So 12 inches equals 1 foot, or 12 inches over 1 foot, or 1 foot over 12 inches. Does anybody know off the top of their head inches to centimeters? 2.54. 2.54. So it's 2.54 centimeters is equal to 1 inch. So 2.54 centimeters over 1 inch, or 1 inch over 2.54 centimeters. All right, so all three of those represent the same thing. So when you do these problems, when you solve problems like this, always ask yourself that question, literally out loud, if possible. Are the final units correct? And this is why one of the problem-solving strategies is to take your, whatever the prompt is, if it says convert into kilometers, write kilometers at the end. That way you know where you're supposed to be going. And when you get to the end, maybe you don't even have to ask yourself. Also consider whether the magnitude of the answer makes sense. And at first, for metric units, it's not going to be super easy to remember that like a kilometer, well, kilometer being close to a mile, it's like 1.6 kilometers per mile. That's a little easier to remember, but like centimeters, or if we do like decimeters or something, or millimeters, those are a little bit harder to remember. But if you end up with, converting something from feet to miles, if you have 5 feet, that's a very, very small amount of miles, right? So your number should be, if we're going 5 feet to miles, that number should be small. So if you get a big number, you should say, hold on, that's not right. So when possible, and like I said, conversion factors can be inverted or flipped because they're equal to 1. So this is a strategy I'm going to use throughout the semester called a solution map. And it essentially does what I was saying, where you write, you write what you're trying to get to at the very end, but you also write what you're given at the beginning. And then you try to make the jumps in between without actually doing any math to bridge the gap. So for unit conversions, our solution will focus on the units and how to convert from one unit to another. So if we had something going from inches to centimeters, we wrote down this conversion factor earlier. It almost doesn't matter like what number of inches we're given here, because we can use this conversion factor, specifically written, again, with the inches in the denominator matching here, so they cancel. But we can convert those. The solution map then going from centimeters to inches uses the same conversion factor, but inverted or flipped. So this is the most important thing, is to, let's use a different color, this is green. Identify the starting point, the given information, and pull that out of the word problem. Don't leave it in there, take it out, because sometimes the words give you hints, most of the time they're just filler, or I will write word problems to make them more interesting. Like last semester was like how many Bitcoin you would need to mine to build a rocket ship better than Jeff Bezos's. Just to give it flavor. And then you want to identify the endpoint. So where are you trying to get to? And then devise a way to get from the starting point to the endpoint. And really what that means is solve the puzzle. Because you're going to have, especially on the unit analysis worksheet that's due Friday, you'll have a whole table of conversion factors. And so when you have a problem, go through and say, I'm starting with units of inches. Identify all of the conversion factors that have inches in them. Those are the only possible ones you could use. And then work your way from there. So with every unit, like these are the ones that I have that I can use, just like the cards, and work your way through it. And then you can use the solution map before you start doing any of the math to diagram out where you're going step by step. But we'll just skip over here. Okay, yeah, so again, more generally, sort out your information, what you're given, what you're trying to find. Then you do the strategy where you do the solution map. try to find which conversion factors you can even convert to and from. Then you solve it by carrying out the math. And finally, check and ask yourself, did I solve for the correct units? And does the magnitude make sense? Is it too big or is it too small? And then do the number of significant figures. All right, so centimeters to inches, fairly simple one. And again, we want to extract out this information first. So if you want to write that you're given 56.0 centimeters, because that 0.0 is significant. Then for a solution diagram, oh, and then what we want to ask, given, and then what's the specific word that I used? I guess endpoint? Oh, find. There we go. That's what I was looking for. So find inches. So our solution map, even though you could probably guess what this one's going to look like, start with centimeters. And we'll say, okay, well, we want to get to inches. And in this case, we know, because we've been doing a lot of centimeter to inch conversions, there's going to be one step in here. And that's going to use, and so this is where I would say, go back to that, let's see, oh, I should have pulled it up. Let's just flip back here, right? So we want to go centimeters to inches. So let's identify in this list, if it's in here. And here's where it helps to say, well, we can exclude mass and volume because we know inches is the length. So we're just working with this section. And look, there's inches and centimeters, right? So in this case, if we find centimeters here, then we know that inches is what we're going to be able to get out of this conversion. And that's the only step we'll have to do. So it's going to be 1 inch, 2.54 centimeters. And then the math here would be, we can put 56.0 centimeters, and we're going to multiply. So it'll be 56. Come in. 56.0 divided by 2.54. And so we'll get 22.0. Well, here, I'll write out more units. So 24.47, right? More units than that. But now we need the correct number of significant figures. So we would round this down to just 3. Because there's a trailing 0, but we have a decimal, so it's significant. So our final answer would be 22.0 inches. And it is important to include that 0, because otherwise you don't have enough significant figures. Any questions so far? Yeah.
So you went around the 7 to the 4 and then take the 5 and move the 5 to 0.
No. Yeah, you're only concerned about the next digit after your last one that you deem significant or determined as significant. Yeah. Any other questions? Cool. So we want to do now 5,678 meters. Again, this is not particularly complicated word problem, but we're given 5,678 meters. And we want to find kilometers. So then our solution map here, solution diagram, be meters, and eventually to kilometers. As you start working through these, you'll sort of get a feel for how many steps there are going to be in between, but you can put too much space right at the very end, maybe not even in a box like this. Eraser, please. Let's say like eventually you want to get to kilometers, but we're starting with meters. And so at that point, you go to your table of conversion factors, sort through those and find which one fits. I don't think this is going to be on there actually. Yeah, it's not on here because Kilo is a SI prefix, meaning 1,000. So 1,000 meters is equal to 1 kilometer. The kilometer, so it's 1,000 meters. So with that in mind, we can just say, oh, okay, this is just going to be one step. We're going to go straight to kilometers. We say that we have meters, so we want to cancel meters out. So this will be over 1,000 meters. And on top, we'll have our 1 kilometer. Then we can plug in 5,680 divided by 1,000. Oh, sorry, left off meters. And we'll get 5.678 kilometers. And here, because we have 4 significant figures, our final answer has also 4 significant figures. Okay. So most of the problems we did last week were multi-step conversions. And more often than not, I think they will be, maybe not early on. But we'll follow the same procedure, but we'll add a few more steps, right? So instead of just finding one conversion factor, we need to find 2 or more. And we'll just add those into the solution map as we go. So let me make sure this isn't, okay. So if we have this example problem here, we're given 194 meters. We want to find feet. So like I was saying before, we can say centimeters here because that's what we're starting with. And eventually, in a number of steps, we don't know how many, we want to get to feet. So for our first step, we can say we got centimeters. I should really bookmark that page. I should bookmark this one too. So if I go back to here, we're starting with centimeters, right? So we know it's centimeters, so we know we're working in units of length. So again, we can ignore all these. And we see we've got 2.54 centimeters an inch. Oh, I should book this. There we go. Okay, so if we have, you can throw that in here. We're going to go centimeters to inches. Which doesn't get us all the way to feet. But we can use growing up in North America to help us out here because we know that 1 foot is 12 inches. So we know that we can convert from inches to feet, which is what we ultimately wanted to end up with. So this will be 1 inch over 2.54 centimeters. And then over here, we'll have 12 inches is 1 foot.
But I feel what if I on accident, I could put 12 inches on top and 1 foot on the bottom or no?
No. So if you put 12 inches on top and 1 foot on the bottom, then you wouldn't cancel out the units of inches.
Okay.
Yeah. So you can solve this 1 step at a time if you want. So if we put 194 centimeters, right, we're going to multiply that. And then we'll get some number that will be in inches in this middle box, sort of this section here. But we don't have to stop there and then do the next math or do the next calculation. We could just say that we're going to also multiply by this other conversion factor. The way I like to do it is just multiply all of the numbers on top. So if I type that into my calculator, it'll look like 194 centimeters. And I'm going to write these in for the sake of example, but you don't need to include the inches or the ones, right? So 1 inch times 1 foot and then I'll hit divide by 2.54 centimeters, divide by 12 inches. And then hit equals. There's a couple different ways you can do it though.
Like last week, would you be able to multiply the bottom, then divide?
Yeah, so you could multiply everything on top, set that aside, multiply everything on the bottom, set that aside, and then do that final division. That works too.
Okay.
You could do 194 times 1. So 194 times 1, then divide by 2.54, then multiply by 1 foot, then divide by 12 inches. It's confusing because there's too many ways to do it. And we won't even bother talking about parentheses. So 194 divided by 2.54 divided by 12. This will be 6.36. Just make sure if you're doing the method where you write out the top and the bottom separately, that you either take advantage of the, will you be able to use the answer key? Make sure you write out enough decimal places that way, so you're not rounding in between those calculations. So with too many decimal places, it's 6.3648 feet. But because we started with 3 significant figures here, we'll end up with 6.36 feet. Grab my water bottle again. Good, making good progress. Any questions on this so far? All right.
Yeah, thank you.
Okay, good. All right, so if we have a recipe that calls for 1.2 cups of oil, how many liters of oil is that? So this is one where, we've added a little bit more to the word problem, but again, pull out everything that you're given and everything that you're trying to find to simplify things. So we're given 1.2 cups. So we want to know how many liters. Cups, I don't remember how many cups there are in a quart. Okay, so we're given this. We're going to say that we have cups. Eventually, we want to get to liters. Our first step, though, we are given a hint that there's 1.057 quarts in a liter. I think there's 4 cups in a quart. Nobody bakes enough to know. Hey Siri, how many cups are in a quart? Yeah, it's 4. Thank you. Now go away. All right. So we can go from cups to quarts. Again, on the unit analysis worksheet, you are given a table that has everything that you need. So if you can't find it in there, look again, or maybe you're going down the wrong path. So we can do cups to quarts. And then we're given this conversion factor over here, which shows us that we can convert from quarts to liters. And then that matches what we were looking for. So our cups to quarts, we have 4 cups for every 1 quart. And then we have 1.057 quarts for every 1 liter. So we can plug in what we're starting with, 1.2 cups And then we're going to multiply these, get our final answer. So do 1.2 divided by 4 divided by 1.057. 0.283. Right? Too many decimal places. So our final answer needs to have how many significant figures? 2. Thank you. So we start with this leftmost non-zero number. And then that's our first one, so 8 will be our second, so it'll be 0.28 liters as the final answer. I think the best way to approach these problems is to treat it like a puzzle. There's a correct answer. You just have to search through the puzzle pieces to find the one that fits. And you can determine what's going to fit because the units match, right? So you convert from cups to cups, and then from quarts to quarts, you get liters. Or cups to quarts, yeah. Another one. So again, we're given a word problem. Are there questions? Can answer questions. I can also talk over murmuring. A running track measures 1,056 feet per lap. To run 15 kilometers, how many laps should you run? So this is a trickier problem, but let's write down what we're given. So we're given that a track measures 1,056 feet, and this is key. We hear feet per, or we hear per. That means almost always that it's a conversion factor. So it's feet per 1 lap. So every time you go around the track, you're running that many feet. We're also given 15.0 kilometers. And we want to find laps. Where should we start this problem? Which unit should we start with? 15 kilometers. Why wouldn't we start with 1,056 feet per lap? You're right. Well, because we're not looking for 1 lap. It's a conversion factor. Yeah. So I think you're all on the right track. So the idea is that you almost never, there are a few cases where you start with something that's a conversion factor. If you remember on the workshop, there was a problem like miles per gallon. We wanted to convert miles per gallon to kilometers per liter. Most of the time, though, we will start with the thing that's not the conversion factor. But also, you're right, because let's do the solution map. We have kilometers, and we want to get to laps, right? So if we start with kilometers, then we can say, oh, well, we have this as a conversion factor. It's not the only thing that we need, but we can use this along with some other conversions, because if we can get to feet, then we can convert from feet to number of laps. So let me go back to that page and maybe we'll have a, okay, so we do feet. So we're just looking at this, right? Again, we're working in lengths. So we have kilometer here, and that's 1 mile, or that's, sorry, not 1 mile, but we do kilometers to miles. So it's probably a good place to start.
Does it give you the miles to feet conversion?
Oh, did it? Oh, yeah. Yes, so we have miles to feet. And then that's not what I wanted. What am I going to do with it up there? Okay. Right, so we do have the miles to feet conversion here here as well. So that's going to be helpful. And And then based on this chart, again, we can do kilometers to miles. So let's start there. We can go kilometers to miles. So if we have kilometers here, we can do miles next. And then we know if we get to feet, we can get to laps. We're given this 1 mile is equal to 5,280 feet. So we know that we can convert from miles to feet. And if we can convert to feet, then we can convert to laps. So, and it might help, if it helps, definitely write these conversion factors in as you go. You don't have to like write the solution diagram out and then write them all in. So we want to go 2 miles. So it's going to be 0.6214 miles over 1 kilometer. And then to go from miles to feet, we're going to put 1 mile on the bottom, maybe 5,280 feet. And then to go from feet to laps, we want to cancel out the feet. That's going to be 1 lap. Whoop. 1 lab. And then we're starting with 15.0 kilometers. Calculator. So now we'll get 15.0 times 0.6214 times 5,280 divided by 1,056. So if you are curious as to how I type it into my calculator, 15.0 times 0.6214 times 5,280 divided by 1,056. 46.605 laps. But it's too many sig figs. So we got to trim it down. We started with 3. Again, we have a trailing 0 with a decimal place. So this will be 46.6 laps, which will actually get you just shy of your 15 kilometers. I was reminded of, I think it was a TikTok, where this person was running on a track, and this guy is always there running on the track, and Strava will like ping if you're like running next to somebody, so you can see their profile. This dude he runs like 200 miles a week on the track, just doing laps. It's real life Forrest Gump. Okay, any questions on this though? Okay. So again, this was an example from, there was an example that we did last week in the workshop, but sometimes you have to convert the numerator and the denominator, right? So the top half and the bottom half of a fraction. And it's not that tricky. You just got to remember that you have to put units opposite to cancel them. So if we have a Toyota Prius that has estimated gas mileage of 48 miles per gallon, again, per meaning divide, right? We can do, or given, actually, I'll write that right now, given 48.0 miles per gallon. But in Europe, they use kilometers and liters. So if we wanted to convert this, then we need to convert both the denominator and the numerator and the denominator. It actually doesn't matter which order you do this in. We can write a solution diagram. So if we're starting with, I'm like thinking about a good way to do this. I think the best way is to write it as miles per gallon. Now remember that we're working with one part at a time. So let's just do miles first because they're on top. So if we want to convert we'll convert miles to kilometers. And our resulting units here will be kilometers per gallon. And then if we want to convert gallons to liters, we're also given that here in the question. And then we'll get, actually, I didn't write what we're trying to find, which is kilometers per liter. We'll get kilometers per liter here. So going from miles to kilometers, miles is on top. So we need to, in order to cancel it out, we need to put miles on the bottom. We'll take our 1 mile is 1.609 kilometers. And then to do gallons to liters, since it is in the denominator, we put gallons now on top so that it's opposite in the fraction. So this will be 1 gallon, 3.785 liters. And then we're starting with 48.0 miles per 1 gallon. And then because this is right 48 per 1 gallon, we can just treat it as 48.0. So do 48.0 times 1.609 divided by 3.785. So we get 20.40475. This will be kilometers per liter. But if we want the correct number of sig figs, we'll round this down to 20.4. You can also write this as kilometers per liter like that. I read that wrong. There's 14 more slides. All right. So what else do we have to do here? Okay. We can talk about density in lab. That'll be fine. So solving unit conversions in the numerator and denominator. Again, so a car is driving 65 kilometers per hour. What is the car's velocity in meters per second? So again, we're given 65 kilometers per 1 hour. And we want to find meters per second. Make this twice as tall. So this is going to be, we're starting with kilometers per hour. We can convert the top or the bottom. We're going to go kilometers to meters. It was easy enough. Again, we've got the hang on those SI prefixes. Kilometers to meters. So we'll get meters per hour here. There's going to be 1 kilometer is 1,000 meters. And then if we want to go from hours to seconds, let's just do it stepwise. So there's, we're going to keep meters the same here, but if we want to go from hours, then minutes first. This is minutes. Then in every, right, we're going to put 1 hour up top is 60 minutes. Because hours here, cancel out with the hours here. And then we can go from minutes to seconds. So we've still got meters on top. 1 seconds on the bottom now. For every 1 minute, that's 60 seconds. So you could, if you know that there's 3,600 seconds in an hour, you could do that conversion. Right? So you kind of made a conversion out of 2 conversions and saved yourself some time maybe. So we're going to start with 65 kilometers per hour. We'll do 65 times 1,000 divided by 60 divided by 60. So we'll get 18, 2 sig figs here. 18.05. It's repeating. With 2 sig figs, we'd be left with just 18 meters per second. And again, you could write it out like this, or you could write out 18 meters per second. Any questions? Oh, that means repeating. Sorry, yeah. Yeah, there's a line over that. Usually there's like 2 digits and then a line written over the top means that it's just always 5s for the rest of forever.
Wait, you said we would have to put them opposites together as well, but the meter stayed on top because there's no further.
Yes,
Or
right. Yeah. So we converted meters up front. Once we were done with that, then we don't need to convert it, but carry it along so you don't forget that it's still in there.
right.
So
Oh, go ahead.
the answer 18.05? Or is it the? Oh, okay.
It's really either of these, the same thing. Yeah, because we started with 2 significant figures and with 2. All right, one more to talk about here. So units raised to a power. Remember, this was the tricky first problem on the back of the unit analysis workshop. And the trick really is that when you're converting from something like centimeters cubed to inches cubed, you have to treat this unit cubed as a stack of 3 units. So you can't just convert once and remove it. That only removes 1 of those 3 in the stack. So if we wanted to convert 1 centimeter cubed, 2 inches cubed, we would have to either do this conversion 3 times. So inch over 2.54 centimeters times 1 inch over 2.54 centimeters. Right, so we do it 3 times like that. Or we can truncate this whole thing and we can do lost my pencil. 1 inch over 2.54 centimeters cubed. So the cube in this case is going to apply to everything inside. So after we've applied this cube, 1 cubed is just 1. But this is now inches cubed. 2.54, it's cubed, so it's 2.54 raised to the 3rd. Is now 16.387. It's a bunch of digits there. And then centimeters cubed. Now, one reason to do one over the other is because these decimals kind of just go out for infinity. So you lose a little bit of precision over doing this, unless you keep the number in your calculator. So you keep all those decimal places.